what we see is a clear change going from 8 Kelvin to 700 millikelvin to 100 millikelvin on the 111 brag peak. So let me remind you that almost every kind of ordering on the power core lattice is Q equals 0, so that magnetic peaks show up on top of nuclear peaks, which actually makes it quite difficult to see them often, especially in a powder sample. So we had to count a lot and be very careful about this. But you can see it even here in the raw data that there is this increase at 111. And taking a difference between 700 millikelvin and 8 Kelvin, there is a peak there, and also at 100 millikelvin minus 8 Kelvin, there's a peak. Similarly, there are other peaks that we measured. We were able to get 5 zone centers, and we could see increases at 111, 113, and 222. So now, let me show you some of the full, I guess you could say, diffraction pattern, except it's elastic scattering, and we selectively picked zone centers here. So we had 5 zone centers. This is at 8 Kelvin, and this is just to show you that this is the same sample that we measured at NPDF on a real powder diffractometer. And you can see the signature of the stoichiometric sample, which is that the 311 is greater than 222. That also persists here. And when you subtract that data from the 100 millikelvin data set, what you see is these peaks that I was mentioning coming up at 111, 113, and 222. But you see a lack of peaks at 002 and 220. So you can actually perform a refilled refinement on this data set, which does include the effect of the error bars associated with the subtraction, which I have not put on this plot because it kind of muddles the plot a little bit. But there are significant error bars here, and that's included in this refinement. Okay, so what we end up with when we do this refinement is that the best fit is the so-called splayed ferromagnetic state, where if you can imagine a collinear ferromagnet with all the moments along Z, the crystallographic Z-axis, then you cast those moments away by an angle theta, in this case towards the spin ice direction. And that angle we have determined to be 14 degrees plus or minus 5 degrees from this refinement. And the ordered moment is 0.9 Bohr magnetons, plus or minus about 0.1 Bohr magnetons. So the size of the ordered moment is actually fairly consistent with what other people have seen. And the splaying angle, as far as I know, this is one of the first determinations of the splaying angle in ytterbium titanate. Another thing to point out is that this is a long-range ordered structure, at least to within the Q resolution that we have on spins. So we know that the correlation length has to be greater than 80 angstroms. So a natural thing to do then is to see whether this correlates with the phase transition. And interestingly, all we see is a very gradual decrease of intensity as you go from the lowest temperatures up to, say, 700 millikelvin. And if we just plot the specific heat here, this is an important point, so it has to have flames, you can see that this is where you would expect a sharp change in the intensity of the peak, but we don't see that. And this is actually the same temperature dependence that we get for the diffuse scattering in the single crystal near the 111 peak. So this is an odd result. And one thing I want to point out is that it is a first order transition, and we are measuring this on warming. So you might think there could be some hysteresis, but this is quite a large amount of hysteresis if that's what's causing it. And so this is, I think at this point, sort of an unexplained result. So just to summarize the elastic scattering, there's you might think about this collinear ferromagnet, which I think most people sort of assumed was close to the ground state for ytterbium titanate. Ytterbium stannate has been shown to have a splayed XY-like ferromagnet where theta is negative 10 degrees. So that's something that's been determined by diffraction. Now, ytterbium titanate, we believe, has this ice-like splaying with a 14-degree splaying angle. Furthermore, we have about 53% ordered moment, and there's no sharp onset of the elastic scattering at the phase transition. So now let's take a look at the inelastic scattering. So this is the time of flight measurement on the disk chopper spectrometer. Here is the pattern at 8 Kelvin in zero field. This is all in zero field, by the way. We never applied a magnetic field at all to this sample, as you probably would not want to do since it's powder. And that can cause some problems. So what we have here is the zero field, high temperature SQ and omega. And then as we cool down to 2 Kelvin, which is about the mean field interaction strength of the material, you'll see the development of some scattering here near Q equals 0. And then going further to 800 millikelvin, not a whole lot changes. Maybe you can start to see some changes building up here. 300 millikelvin, I think you can start to see a pattern. There's not really much happening. And then at 100 millikelvin, nothing happens. And this is going from 300 millikelvin to 100 millikelvin is going through this sharp first order phase transition. So taking a look at some of the energy cuts here, we've shown here the low Q integrated energy cuts. So this is in mod Q, this is powder average. Yeah, so going out in Q, you start to see a change from what looks like a quasi-elastic energy dependence to something that has more of a broad plateau as you go out in Q. And again, this just serves to highlight that for all of these low temperature line shapes, there's really no change in the SSQ and omega going up to 2.5 Kelvin. You only start to see a change as you go beyond that. One thing I'd like to point out is that if you were to take the exchange parameters, for example, the ones that we determined in this paper in 2011, and calculate the zero field ground state and the spin waves from this ground state, what you would find is a splayed ice ground state like the one we found, but with a much smaller splaying angle. And you would also see this gap of about 0.2 millielectron volts to a single magnon dispersion. We clearly do not see that. I think it's instructive to look at the line shapes compared to the crystals. So this was a data set that we presented back in, I think it was 2011, on the single crystal that I showed you before that doesn't order. And we looked at the the energy dependence in different regions of the HHL plane. And what we see is that when you're on this diffuse rod of scattering, there's this quasi-elastic line shape here that extends out past about 1 millielectron volt. And then if you go off the diffuse scattering into one of these more dark regions, you don't see this quasi-elastic signal. You see this kind of plateau, which is around 0.5 to 0.6 millielectron volts. And the same kind of signatures are seen in the powder. So here is the low Q integrated signal. It looks very similar to the on-rod scattering. And as I mentioned before, it doesn't change at all from going from 100 millikelvin to 300 millikelvin to 800 millikelvin. And as you go out further in Q, you see this plateau, which is around the same energy of 0.5 to 0.6. So this suggests that the line shapes are basically, for all intents and purposes, independent of the specific heat. Not only do they not change as you go through this first order phase transition, but they also don't seem to depend on the whether it's a crystal or a powder, which we know have very different specific heats at low temperatures. And so that's a puzzle, I would say. Finally, I'd like to point out that ytterbium spanate is an extremely related material. And the only difference is that you change the non-magnetic B-site cation. And this unfortunately means you can't grow single crystals of this material because SnO2 is very volatile. But the powder samples have been investigated, for example, in this PRB from 2013. And what they found, and what other groups have found, is that there's a splayed ferromagnetic ground state similar to the one we've seen in ytterbium titanate, but with the opposite splaying angle.